everyone. Great to be here. We're going to try to do this without a microphone, so can people in the back hear okay? It's not a giant room. Before we talk about me, I want to learn a little bit about you guys. So can we do a quick little poll? People who are on the engineering side. So it could be web, it could be mobile, it could be whatever. Okay, great, hands down. Design, are there specifically people with those backgrounds here? And everything else? Okay, great. So we got a good group, good mix of people. I actually see some familiar faces from the kayak talk. Fortunately, there's some new material tonight, so hopefully we'll have some new learnings. So by background, I am an engineer. I'm currently co-founder and CTO of a company called Fritz. We'll talk a bit more about that later. I've done a lot of different stuff in the Boston tech scene over the last decade, starting with a job at HubSpot, where I helped build that company, and then went on to do things at Jana, Babaco, a company that got acquired by Airbnb called Whip. And I'm currently a mentor in the Techstars program, so that's starting up, I believe, next week. But if anyone goes through any of the Techstar programs, you may see me around the offices there. We're going to start with the state of AI. So we're going to talk a lot about AI applications and ways that you use it, but I want to talk really broadly about where we are currently at with AI. And I think if there's one point I would like to drill home for everyone, it is that AI has moved well out of the moonshot category. We are no longer looking at this technology as something that will happen in 10 years. We're seeing it work today. The roots of AI in deep learning and machine learning go back to the 1970s. That's when the first scientists started putting together the concept of an artificial brain and saying, well, this is how a neural network would work. But we didn't have all of the power in order to use it. And we've caught up. We've gone through, in the last 5 years, probably the most incredible acceleration of any sort of new technology coming online, where we've got all of the data in the world that we need to collect through the big data systems and clickstream pipelines and things like that to train machine learning models. We've got the architectures, so starting with the work done in the 1970s, all the way up to the most recent research you're seeing coming out of schools like Carnegie Mellon and Stanford for brilliant architectures to be able to teach computers how to think and how to adapt. And we're finally getting around now to doing all these interesting training things. So some of you might be familiar with products like Data Robot or something, where you can now train neural networks on what your business is doing. Not just broadly speaking, is this thing a dog or a hot dog, but rather, what is my specific prediction I want to make? What are the data that I have, and how do I train an architecture to get out the door? The problem is, we're not done yet. So as you can see, there's a couple milestones still ahead of us. Major deployment. It's still a pain in the ass to build these things and get them out the door and get lots of your users to use them. And the user experience is still awfully clunky. We're in the early days. I think that's best illustrated by looking at a standard adoption curve. I did not invent this chart. People have probably seen this thousands of times before. But the idea is that we are in the very early days of what is probably a multiple decades long transition as AI starts creeping into everyday products and everyday experiences. We're kind of, let's say between 2 and 10% in. It's still very, very early days, so there's a ton of opportunity there. This gets me excited. I like when we're early in the adoption curve. My background is startups and being very early on things. For some other businesses, this might be terrifying. They might be saying, we have a very specific customer who doesn't take bullshit, and we can't give them new beta technology. So you've been warned. Neural networks themselves, the sort of core of what we tend to talk about in AI, are just like software. They are little packaged things that understand how to execute one particular task. They are not multi-purpose. We don't have general artificial intelligence yet. We can't do one model that can figure out everything we want to do. Instead, we have to think about them as little programs, little executables. Now, the old version of software, it was a very fixed thing. You had people who had to write lots of lines of code that would do the exact thing that they predicted ahead of time. Whereas neural networks and sort of the foundational elements of AI are adaptive. We train them on situations, but they can infer in new situations. But the important thing here is that both are just infinitely distributable. If you compare this with a traditional product, like something in the physical world, you can't get it anywhere at any time. You have to think about, shipping it, boxing it, creating a new one, 3D printing it, that kind of stuff. All those are impediments. AI is going to be proliferate. It's going to go everywhere because it distributes like software. In the same way that I can write one version of an application and put it on 1 billion smartphones, you can write one neural network that understands something really well and put it in 1 billion devices. And that's the world we're heading into, is software distribution, but intelligence. And we'll get deeper into this tonight. There's a big sort of umbrella thing for this called Software 2.0. Andre Karpathy, he's the head of AI at Tesla right now. And before that, he was a researcher, and I think he was at Google before that. But he's got a ton of experience. And he writes about this as sort of a transition from having a software developer just try to sit down and hammer out all the conditions that they can figure out to something where we just train more adaptive spaces. So instead of explicit instructions, we go to goal behavior. What do you want to happen? Not what are all the steps to get there. If you're thinking about like a giant decision tree of if-then-else statements, we're now moving to small little brains that are like, I know how to handle this one situation, and if I don't know how to handle this situation, I at least can fail in an intelligent way, or I can move forward. Or I can like raise my hand and say, I need to learn more about this. Save that condition so I can go back and train on it again. This is a blog post, Software 2.0, if you Google it. I encourage those of you that are on the engineering side to check it out, because it is going to fundamentally change the way that you do your job as a software engineer. Maybe not this year, but over the next 5 to 10 years, if you're not really familiar with how intelligence and adaptive technologies work in software systems, you're going to have a bad time. The platform theory comes into play with AI because we want to look at AI as a thing where value is generated by the applications as opposed to by the technology itself. In traditional platform theory, you take something like Microsoft Windows. The value of the company Microsoft should be less than every company that was built on top of their technology, right? So creating a piece of software that runs on Microsoft Windows, if you add those all up, you should aggregate more value in the platform itself. This is not true in other spaces. There are certain products like Google Search, where everything you get to through Google Search might still not add up to the amount of money that they made sending people there, right? Those companies that are giving you the end piece of product, they don't make anything by Google sending you there. So that is not a typical platform theory. But I believe that the world of AI and ML is going to be. We're seeing a technology just sort of out there as a layer, but all of the interesting stuff comes on top of it. It's all the intelligent capabilities that are going to be built using AI and ML that are valuable, as opposed to just AI and ML themselves. And we'll get deeper into this too, but just broadly speaking, I wouldn't think that the company that creates the best architecture for a neural network is going to win. Nor is the company that creates the biggest server cluster that runs AI going to win. Instead, it's going to be all of the intelligent capabilities that are created using those things. This is one sort of concrete example. This is cutting edge. We're not there yet, but for the engineers in the room, if anybody went through computer science training, you have to learn how databases work. And for those of you who are on the engineering side, a database is just a bunch of files. That's really all it is at the end of the day. You put a file on a computer and you say, okay, I want to index it by the first word in that file, and you write another file that has all those words, all those first words in an order, and then you can look up where those files are. That is a very inefficient way to store and retrieve information. It's the best way we could come up to when we said, well, we don't know how to make things intelligent. We don't have a person that's a librarian, so instead we'll just write down in files where you look everything up. This is research that shows we can teach neural networks to be that librarian. We can essentially take all of the information, pass it through a small brain. The brain decides where to store it, and the brain decides where it stored it. And as long as those two things converge, you end up getting incredibly fast retrievals. So you end up seeing major speedups by using learned indexes over things that are actually looked up on file. And that means you're going to have the ability to have much bigger databases, more fragmented storage without penalties in terms of space, that kind of stuff. These things are not widely distributed yet, but I would expect over the next few years you're going to start seeing variants of Amazon services or Google services where their database has AI, and this is the kind of thing they're talking about. So 10 years from now, I think it's always fun to look out a ways and figure out where we're going to be. If today everything we have is enabled by technology, or software, I should say, from our cars to our microwaves, I think the path forward looks like everything is going to also have intelligent capabilities. It doesn't obviate the need for the operating system or whatever the application is that's in your microwave, your car that, I like to say like the popcorn button on the microwave. Today, it's executing instructions. Turn the microwave on for 2 minutes, do this thing. I believe that at some point that will be an intelligent capability. I don't think that's the most expensive thing that people should be working on today, but at some point the popcorn button should just know when your popcorn's done popping. Whether that's through a camera or a microphone or a sensor or something like that, we can train a small neural network that can be easily stored on a microwave to do that. And I think in that case, anything that's intelligent will beat anything that's not intelligent. So we will start to see entire waves of products that just push other ones aside through only intelligence. this thing is a little bit smarter than that thing, and we're going to watch these waves of technology accelerate. We're going to watch the cycles like push new products in and out faster than we were before. History repeats itself, but it gets faster. So we're going to start seeing intelligent things come on the market, and then we're going to see more intelligent things push those things off the market, and it's going to go round and round and round. And that means there's incredible opportunities. That's why I work in this space, because I can't see any other transition that's as exciting and will open up as many new doors as the first realm of intelligent things coming on, and then all of the subsequent waves that come after that. So that's where we are in the state of AI. But I'm going to talk a little bit about edge intelligence, because that's where most of my focus is these days. And let's define a little bit about what edge actually is. So traditional AI machine learning is you've got a bunch of information. So you've got sensors, you've got analytics, you've got data, and you send that stuff up to the cloud, and the cloud aggregates it, counts it, trains a model, receives the information to make a prediction, sends the prediction back down. This is kind of hard to read, but that says speed, privacy, data, cost, UX. Those are the things that are bad. In a traditional world where you don't push the intelligence down to the edge and you have a sort of cloud-based intelligence, where you have to run everything through a server round trip, it gets slower, you're giving away data, which might not be down with people's privacy policies, it might be illegal in some places. The amount of data you have to push back and forth can become ridiculous. The cost, the user experience tends to suffer. All of those things get worse when you have to push information up and wait for it to come back down. Not to mention, if we're talking about certain use cases and what I like to call 60 frame per second problems, you're just not going to be able to do it. If you want to create a self-driving car that doesn't routinely crash into things, an internet connection can't be part of your dependency chain. You have no time to send things up to a cloud. Everything has to run there. So that is what edge intelligence is about. It's about pushing the trained models and the actual capabilities down to where they need to be. So it looks like a self-contained cycle of analytics, intelligence, processing, prediction, all happening in one place. You capture an image or a frame of a 60 frame per second video, you infer what's in it, you act on it, and you repeat. And that type of thing is what edge intelligence is all about. We are moving from world of, so on the right-hand side there, that is a Google TPU pod. Google spends a stupid amount of money on this stuff. They have built a custom chip called the TPU, which is called a Tensor Processing Unit, that's what TPU stands for. And they rack hundreds of these things, and they spend millions of dollars to rack them. Also, they can do little stuff like predict what link you might want to see ranked at the top. Like they do very, what you would consider sort of routine predictions, but they make these giant clusters to do it. And we're moving from that, running your AI and your ML, to this, which is just a very small microcontroller. This is like a microcontroller that costs $5. And those can be in all sorts of devices. They're in everything from, well, cell phones have fancy versions of this, to microwaves, to lawnmowers, to basically anything that has an intelligent, charging capability and knows when to turn itself off. There are microcontrollers everywhere, and that means we're going to move the intelligence down to those microcontrollers. So if there's thousands of TPU pods, or if there's millions of processors in the cloud that are available to you, there's going to be hundreds of billions of microprocessors available to you. The capability to process on them is not the same, but we'll talk more about how you get around that. It's rather that there's a lot more use if you push the intelligence down than if you have to push all of the information back up. So when I think about edge intelligence, it's really like, don't send the model, or don't send all of the data to the model, send the model to all of the data. Creating a real world copy, or a copy of the real world and sending it to the cloud is kind of dumb. But that's what we do today. So my prediction, maybe bold, maybe not so bold, is that edge intelligence is going to win all of inference. And in machine learning, there's sort of two phases. There's training, where you take a huge corpus of information and you make the intelligent model. And then there's inference, where you take one new piece of information, you run it through the model to predict what's going to happen. So you do that sort of inference mode. I think all of the inference is going to end up on the edge. Or not all of it, but if you look in terms of raw numbers, the hundreds of billions of devices doing predictions are going to add up to a lot more inference than what's currently happening in the cloud, or what would even be capable of happening in the cloud. If you think about just something as simple as well, not simple, but like a self-driving car, the number of predictions that's happening in one of those things on one sort of routine trip is staggering, and that is edge intelligence. That is happening out where the world is, not up in some cloud. Okay, so let's get to applications a little bit. We are still early days. We're going to get to a place where you can do a lot more complex things than this. But this is a formula I like to give to say, here's a practical approach to thinking about how you can apply AI to a problem, how you can actually build an application. And what it means is take a sensor. So take something that's on a phone, for example, a camera, a microphone, an accelerometer, and combine that with an expert for 1 minute. So what can you do with 1 minute of someone's brain and a sensor? And we're going to get into some detailed examples of this. Vision. This is a camera sensor. That's a very big looking one, but this is the kind of thing that everyone has in their pocket right now. And these are the applications that you probably also have in your pocket right now that are running AI. They are running neural networks. They are intelligent applications that are already widely distributed. So Snapchat has built a huge reputation on face filters, on putting masks on people's faces, or manipulating sound, or manipulating the background behind you. All of those things are based on neural networks, and they run on the phone. That's how you can use it in live video mode. That's how you can put it in selfie mode and actually see what you look like. If you had to send that experience back to the server, it wouldn't be very much fun. This is an example called Style Transfer in the middle from Instagram. That takes the picture that you've just taken or on your phone and uses a small little model trained in different artistic styles. My company, we do a bunch of these based on like artist work, so you can kind of do like a Van Gogh style or a Dali style, that type of thing. And they're little intelligent models where you say, just re-envision what we already know through someone else's time. So sort of like if you had a really quick version of a painting, you know, by Van Gogh. Like, you take this portrait, kind of make it look Van Gogh-y, they could probably do that in maybe a minute. Maybe more than a minute if you're talking about real paint, but Photoshop could be pretty quick. And then Wayfair does a bunch of stuff with augmented reality or mixed reality, where you can actually put an item in a room. And this has some interesting things going on. So there's obviously the plane detection. It has to know like where the floor is, and that's a neural network. But there's also a lot of spatial awareness with the way that you move the phone. So if you're doing this in video mode and you move around, it's using the accelerometer to figure out how you have shifted your position from where you originally placed the item to figure out depth and pitch and yaw and move everything around. And that stuff is all running, again, on device. It would be a much worse environment if you didn't do it. So sort of, again, back to that sensor plus a minute. You take a camera, you take a minute in Photoshop, and you can do any of these. You take a person who knows their way around Photoshop, you can do any of these, right? This is something from a company called Mobileye, which was acquired by Intel 4 or 5 years ago. It's pedestrian detection, and you can see the bounding boxes around the kids' like faces, torsos there. It uses forward-looking cameras and infrared to find people, and that is because a machine learning model was trained on what people look like, and then they put it in the car. This, again, like these things just don't work when you have to do round trips. You wouldn't be able to see it. But this is what enables a lot of adaptive driving systems. So if you've ever used adaptive cruise control where it follows the car in front of you, there's a model in there that knows what the taillights in the back of a car looks like. It knows when a new car is moved in front of you and how to adjust to it. This knows how to look at pedestrians. But these types of examples are like, again, a camera, and maybe not even 1 minute, maybe like 1 second, you know? Just draw a box around the person. Where's the person? We've trained these little intelligent algorithms to determine what in this picture is a human, and like, should I stop the car? Should I swerve the car? What should I do? Amazon Go, yeah, some of these are things people may not have seen yet. I went to the store, I'm not sure if I took that picture or not, but I went to the store this summer, and it worked perfectly. I mean, there's hundreds of cameras up in the ceiling, and all it does is track you walking around as like sort of a little entity, and then anytime you take something off a shelf, it detects what that object is, and it combines the two. And then when you walk out, it charges you. So lots of intelligent devices, lots of intelligent models there, but a pretty simple problem for anyone in this room to do. If I just said, follow that person around and tally up what they put in their cart before they leave, like no problem. Anybody can do that. But we can train things to be that smart now, that level of smart. This is a company called Focal Systems. So a friend of mine out in San Francisco started this company. They use cameras on the side of that tablet, they use an Android tablet, to constantly look at store shelves as you're walking around. And they can use that in a couple of different ways. One, they can tell you where the product you want actually is in the store. Not where it should be, where it actually is, because it saw it. These things keep a sort of centralized database of where is all of the product on what shelf in what aisle, even with sort of like micro indoor GPS coordinates. Where is this thing? And that's what you kind of see with the wayfinding path there. How do I get to the thing I want? But they also use that information back the other way to the retailer to tell them, this stock is running low, this shelf is empty, this product's in the wrong space. If the tablet can't reach out and move it for you, they can at least tell a human to go out and do it. And I've seen Walmart pushing out a slightly more complex version of this where they actually have like a, I don't know, like 7, 8 foot tall robot that drives around and just videos the shelves. And that's done the same way. Bunch of cameras, knows what to look for products, knows where it is, can combine those two things in a database and say, this product's not in the right place, or this product is here where I expect it to be, or there's not as many on the shelf as I expect it to be. And these are all, again, sort of just camera-based, very simple systems that any person could do. But why have a person do it? And this is one of my favorite. I'm a big smart home person. I have like 1 million devices, and they're all connected at home, and half the time they don't work, but we're still in the early days. This is a company called Dahlia, and what they are doing is using inside cameras to determine context. So the way to read this is to see that there's a person sitting on the couch here, and that there's a TV that's currently turned on, and that there's a certain like lighting scene. And what they're aiming for is for people to be able to go into their homes, and through cameras, the home determine what's about to happen. So if you walk into the kitchen and you might be going, because it's like dinner time, you might be going to cook something, it'll bring the lights up in the kitchen, it'll bring the lights on in the dining room, it'll bring the lights down in the bedroom because you're not there. This is a situation where like you might want a reading light to come on if that TV goes off. Oh, you're not going to watch the TV, maybe let's turn the reading light on so you can get a little more ambient light around your space. And they're trying to train little intelligence models and just asking, based on this photo, what is happening in the room? Is this person going to read? Is this person going to watch TV? Are two people talking? Should I turn the music down, etc.? And then they want to tie it all into your smart home. So your Philips light bulbs, your Sonoses, that sort of thing. I'm very excited about where this stuff is going, but it's still early. Okay, so that's all the camera sensor. Those, don't worry, we don't have this many examples for all of them. But the camera sensor is sort of where we're currently putting the most work in. If you look at the, one good way that I like to gauge this is I look at all the stuff that comes out of research groups. So I look at the types of papers that are being published from Stanford or MIT or Carnegie Mellon or University of Waterloo in Canada. And I look at what they're working on, and most of them are working on computer vision. And the way that it tends to work is you kind of get this trickle-down effect from researchers get hired by companies like Google who commercializes technology, who makes it possible for everyone else and sort of democratizes it. So if the people that are currently publishing papers are talking about computer vision problems and architectures there, that's probably what we're going to have the most advancement in. The second behind that is audio. We've got a lot of stuff that does natural language processing, and whether you think about it as an AI or not, everybody's phone has text-to-speech and speech-to-text right now. But those things are actually, they're small, capable, intelligent models that are deployed. And the biggest, most distributed versions of this are the home appliances that you talk to. So I don't know anymore what the numbers are, but I had talked to the folks at Comcast, I don't know, 6, 9 months ago, something like that. And they were the largest distributed AI voice platform in the world. The Comcast set-top box that you can talk to is an artificially intelligent model that understands the thing that you're telling it to find and executes the search. And they were in hundreds of millions of households or something like that, or maybe not 100 million, but they were in millions of households. And now Amazon, with its series of Echo devices, they are now over 100 million devices out, so they may have eclipsed Xfinity. But these types of intelligent things are already out there. And if we look at the formula again of like 1 minute of an expert, you don't even need the expert, you could tell almost anyone, find the channel that's playing the thing that I want to watch, and they can figure it out in a minute. Maybe like, anyone over the age of 6 or something. The other cool thing that happened, this is about 2 years ago, this is the Google Pixel 2. I think most people are familiar with what Shazam is, that you would record an audio clip, you would send it up to the server, it would send back down a prediction. Sometimes it got it right, if you were in a live venue, it got confused a bunch. Well, Google challenged themselves to build that just into the phone. So no server here, no round trip, no recording. This is ambient. And ambient is a category that I'm very excited about. We're not going to get into it too much tonight, but ambient is basically the concept of you didn't ask anything to do anything. It's just happening. And what Google did was use the microphone to listen to songs, or what it thought was songs, in a room at any given time. And when the prediction confidence is high, when it thinks, I'm listening to a song and I know what song it is, it just shows you on your home screen. The phone's not unlocked. You're not in an application. That's literally just the blank home page of like, you pick up your phone and it's sitting there. And they do that by taking a database of about 75,000 songs. They figure out a way to encode them all, and then they make the predictions happen down on the device. Uses a little bit of battery. Other than that, doesn't use anything. This is not using a network connection. And it's pretty cool. Once you see it happen, and somebody goes, what song is this? And you just look down at the phone and it shows you what song it is. It's kind of a cool experience. I don't know why this isn't more widely distributed. Perhaps, if you want my opinion, Perhaps because, like, sort of product strategy at Google is whatever someone thinks is a good idea. And then it doesn't necessarily get rolled up into like a business for decades. You know, like Gmail started as like a good idea, and then 10 years later they're like, what if we charge $5 a person? You know, it's like, it took you 10 years to get there? What is going on? But this is something I think is amazing technology. It's just not on every phone yet, but maybe it will be. And this is one that's a little more pragmatic, but everybody who's ever talked on the phone knows that background noise is annoying. You know, can you mute yourself? We can hear the coughing, we can hear someone eating a bag of chips, whatever the hell it is. By using artificial intelligence, they've actually been able to train these little models on everything that's not your signal. So everything that's not the voice. We're taking a look or a listen to a conversation and just mute every single packet that doesn't sound like the person who you're expecting to be speaking right now. And when you put that on the phone and it runs locally and it runs fast, your phone call clarity just goes way, way, way up. So these are little neural networks that they've been able to push down and sit them on the phones, and it just does all this background elimination of noise. Current state of the art is that you have 2 microphones, one near your face and one away from your face, and you cancel out the signals, trying to take everything that's in the background and bounce it against what's in the foreground and try to get rid of all the neutral noise. This works a lot better and is much more intelligent. As far as I know, this isn't in any phone yet. This is just research, but we're getting there. And then finally, we'll talk a little bit about the accelerometer. I don't have a million examples here. Do people generally know what accelerometers are? Yeah, okay. Accelerometer is just this little thing that sits in your phone and it measures 3-dimensional force. So it's like, imagine like a little marble suspended in Jell-O or something, and you can feel how hard the Jell-O's pushing the marble around in all 3 axes. And it samples at something like, I want to say like 1,000 times a second or 10,000 times a second. They have an incredible amount of data that comes off those little guys. Just constantly sampling, where is the phone, what space is it in? That's how you would do something like the lift to wake feature on a new iPhone, use the accelerometer. But this is a company based here in Boston called TrueMotion. There's not any people from TrueMotion here, right? All right, cool. What they do is pay as you drive insurance, and they white label it. So Progressive offers an application that says, turn this on while you're driving, and we'll monitor how you're driving. And based on how you're driving, we'll offer you a discount for being a good driver. And that is running a couple of intelligent models. One that is trained on how all drivers behave, or like how all events look. What is a hard braking event? What is an erratic swerve? What is a hard acceleration feel like? That kind of thing. And then a separate model is trained on you, so they know when you're out of your pocket. If you're a person who normally drives a little bit erratically, they might not be that worried about it. They're like, yeah, we understand the risk around that person already, and we can see that they're in their pocket. However, if it changes, then they want to start getting worried. And right now, the model is sort of flipped, where you use this application and they give you a discount. I'm pretty sure it's going to go the other way at some point, where it's like, you have to use this application and you pay as bad of a driver as you are. So let's all hope that AI cars get here sooner than later so that we don't have to drive ourselves at all. But really cool company, and all based, again, on just the way the accelerometer data works, and training little intelligent models on how do you interpret that information. So there's some problems. We'd be remiss if we didn't talk about ways that AI fails us. I'll just show you one that fails. Yeah, so that's not good. You can imagine bad things happening if you start to think lots of things are rifles. But what's happening here is this is an adversarial network. So it might look like a turtle to you, or to everybody, I would hope it looks like a turtle. But to a computer, the pattern on that shell is very confusing. In fact, knowing a little bit about what model you're trying to trick can help you print, which is what this is, a 3D model that looks like one thing but tricks the computer into thinking another. So I've actually played with these in real life. Some researchers from MIT brought over adversarial turtles, which are just little 3D printed models. And one of them, every model thinks it's an avocado. You know? And in this case, it's a rifle. But you've got the ability, if you know how these models make predictions, to trick them. This is going to be a problem when we're talking about things that can potentially be risky or dangerous or expensive, that if there's going to be some reason for someone to be pushing back the other way, there is a way for them to fight it. We will eventually connect enough data to be able to make these sorts of situations far, far less frequent. But for now, this is actually pretty easy to do. And when it gets worse is when you're talking about things that are dangerous on the road. So I don't recommend doing this, but I do it for fun. Next time you see a self-driving car, if you're out in San Francisco, they don't do them around here, or Arizona, just go like this. Just pretend you're going to run in front of it. Don't get close, because you'll hurt yourself. But just do that. That car will stop immediately, I guarantee you. And the reason is they're looking at a LiDAR circle 60 meters out, and they're creating a vector of how I'm moving. And if I go like this, and it looks like I'm going to run in front of the car, they're just stopping the car. The policy is always better safe than sorry in these cases, which, if you're a passenger, is not fun. And the cruise automation guys, which is what this thing is, fucking hate me because every time I see a car, I do that just to see if the model's getting any better. And the car stops, and they just look out the window and they go, nice job. But it's entertaining, and at some point when these are more widely distributed on the streets, like you'll see it for yourself that a situation that wasn't going to be dangerous is something the car just gives up at. So there are a lot of problems, but we're working our way through them. I want to talk a bit about edge hardware. So if we're looking at AI, it's important to understand how these things get executed, where we're running them, how fast, what type of capabilities we have. And we're currently entering a new age, what I like to call the age of the NPU. So historically, we've had CPUs, then we've had GPUs, now we're going to have NPUs. And these things are all slightly different, which is why we have all of them. There's a Samsung Exynos on the left there. They have a thing called the NPU as part of that. Apple calls it something slightly different, the Apple Neural Engine. But these companies, plus Qualcomm, plus Intel, plus a lot of other companies, are starting to build dramatically different processors that are just made to do AI. So AI type calculations, which are just a bunch of matrix math, are typically really bad on CPUs because they're not stepwise. And if you try to make them stepwise, you end up creating a lot more executions. On GPUs, they work sort of okay, but GPUs were designed for doing large-scale sort of graphical things, so 2 dimensions or whatever. NPUs and TPUs, the Google version of this, are made to do tensor math, which is what the sort of core of neural networks are, incredibly fast and incredible volume, and I'll show you a little bit how. This is a timeline just of iPhones. And iPhones, whether you believe it or not, are one of the most advanced AI-backed consumer products that anyone has ever seen. This timeline starts in 2015. So we could go back further than that, like 2013 is probably the first time Apple had anything that was based on a neural network, and that would have been Touch ID. So when you started unlocking your phone, you were training your phone with a local neural network on what your fingerprints looked like. And then it was executing that in order to determine if that was your fingerprint. The sensor determined that your fingerprint's on top of it. That's not the hard part. The hard part is capturing a little intelligent model that always knows when to unlock for your fingerprint, but not for someone else's. And that was like 2013. But 2015, look just at the hardware side. The Apple A9 chip has a GPU provided by a third-party vendor, a company called Imagination. This is a chip called Power VR. And they added, in that generation, features of Hey Siri and a feature for people and photos. If people don't know what that is, that means you can go into your photo album and say, I want to look at all the photos of Dave, and it'll show you all the photos that his face is in. That's facial recognition technology. Now, they don't want to market it that way because people get scared of that, but that's called people and photos, and that was one of the things that Apple started saying, this AI shit, people are using it. Like, it's actually starting to power better experiences. So then they started plowing resources into this thing. The next generation, 2016, the A10 Fusion chip, which was in the iPhone 7, they built their own GPU. And what they did with that cycle was to make the speed faster and the cost lower. So they went from a GPU they had to buy and put in a system on a chip to a GPU they built with their own hardware team. And then they added portrait mode. So portrait mode is when you can actually see that a person's in the foreground and there's something else in the background. You can do the studio lighting effects, that kind of stuff. They started to create more user experiences based on the AI technology. And they started to invest even more in the hardware capabilities. So these last two are the important ones. The A11 was the chip that came in the iPhone 10. And that was the first time they did Face ID. Now, Face ID is an incredibly complicated piece of AI technology. It is determining how to store a model of your face, not just your fingerprint. And there's a lot more data points and a lot more tricky edge cases to deal with. But anybody here who has an iPhone 10 or 10s probably knows like it works really well. But that is a huge feat of engineering. And the only reason they could ship that is because they built an incredibly powerful neural engine in that generation of chips. So they built a 2-core neural engine that does 0.6 teraflops. And that was enough for them to do Face ID, and for a new feature which was raise to weight. So using the accelerometer to determine this person is picking up their phone, and they're going to want to interact with it. That was The graph's probably not matched quite right, but that was a huge step in capabilities up from the generation before. So you go from like no NPU, still no NPU, but like our GPU is getting better, to actual neural engine, something dedicated just to these AI functions. And now, in the most recent generation, the 2018 A12 Bionic chip, they actually have an 8-core processor that does 5 teraops. So that means, or teraflops, that means that they can do all of the things with Face ID, with Hey Siri, I don't know if I'm waking up people's phones, with portrait mode, with people in photos, plus computational photography where you're actually doing, like you can change the state of the photo after the fact. You can take a photo and then change the f-stop or something like that. And then also opening it up to other developers. So people like me can start writing software that runs on that neural engine. So Apple is making an incredible investment into these NPUs, and that doesn't happen by accident. If they can see all of these use cases, going back to 2013 that people interact with, they probably got a whole lot more we haven't seen yet, and that means there's going to be more and more capabilities. So I get really excited just looking at this and seeing that, like, if a company like Apple that sits at the forefront is investing in this, then I think everybody else is going to be doing it as well. And here's a little data that shows you how everyone else is doing it. This graph is logarithmic, or So this is 0.1, this is 1, this is 10. So if you're looking at the differences here, that is a huge difference. And likewise, same going down. The way to read this is to look over here at the iPhone 10. This is localized at 1. So however fast an iPhone 10 is, that's how everything else stacks up at running a neural network. If you look at the difference between the newest iPhone and the newest Android phone, it's something like a 60 times difference. Apple is that far ahead in that their neural networks run so much faster on their hardware than anything you can buy from a Qualcomm or a Samsung or anything like that. It's pretty stark. Maybe I should visualize this graph in a different way next time, but you can definitely see that there's a pack of things that kind of run together, but then there's some stuff that's outliers, and Apple is just dominant on all these things. This is research that we did at Fritz, by the way. What does this all mean, really? Well, this again, another logarithmic scale. We're looking at Moore's Law, and Moore's Law says that every year or so we should be able to double the amount of transistors in a space and half the cost of doing that. And it was all transistor-based back when the only thing we cared about was the CPU, and it was just like, well, if we can fit more transistors into a smaller space, we can do more calculations. That doesn't always end up being the most useful thing for a developer. So what I think is going to be happening here is that we're moving to a new age of caring more about the operations that are taking place, and that NPUs are going to offer us an extension of Moore's Law. That CPUs are going to hit, they're already at 7 nanometers, they're going to hit a floor at some point, and we just can't make the process any smaller. We start to have atomic inference or interference. And we're going to instead start worrying about can we make intelligent things, and can we give those things incredibly powerful processors to work with? And I think the capabilities will continue to be growing on an exponential scale, even if the chip sizes don't keep getting cut in half. Also, there's you're dividing everything by cost here, and these Apple generation chips probably used to be super expensive, but as you move out, they get cheaper. We'll talk about that in a second. But the way to read this is sort of we're at the end of this with the best GPUs in the world. But I think the best NPUs in the world are going to be pushing beyond that. So that's what we're looking for over the next several years, is what are the capabilities of these NPUs compared to everything else. Prices are a factor. So if you think about how all of these things get deployed into actual devices that you can own, not giant corporate computers, the prices have to be somewhat managed. On the farthest right is a flagship mobile phone and a processor with including an NPU, so a system on a chip that includes an NPU, might be about $120. So the most recent generation of an Apple chip or a Samsung chip or a Qualcomm chip probably costs in the bill of materials about $120, and they probably get a bulk discount. But that's about 10% of the cost of that device. It's a $1,200 device. Those things, a generation later, start becoming more manufacturable at higher scale, and the price comes down. So the chip that's in that middle thing, that's a Nest IQ Cam. I don't know if anyone has a Nest IQ Cam, but a Nest IQ Cam actually will do facial recognition. It'll determine who's in the house and if that's a person that you should send an alert about. As a person who has security cameras, it's super annoying when all you get is a motion alert that something moved. You're like, I don't care if something moved. Tell me if something's wrong. And that's the problem they're trying to solve. But they took a chip that used to be in a flagship mobile phone, and 1 year later, it's now in a $300 camera. So again, about 10% of the bill of materials. And then finally, we're not here yet, but I think the types of chips that are capable of doing really intelligent stuff are going to come down over the course of 2 generations, 3 generations, to like $1 or $2. They'll be like a microcontroller. We don't have to stamp them out with the actual intelligence in it. We just have to stamp in the sort of capability to run a neural network. And that means we're going to do a lot more like voice control and intelligence and things like Dahlia, that sort of contextual camera in the room, all on device for relatively low cost. So 20 bucks instead. And that means we're going to have billions of them. They're going to be everywhere. This sort of makes sense why I'm saying that edge inference is going to be the dominant form of all inference at some point, because this trend won't stop. So I have a little bit of a half-joke law here. So Parkinson's law basically says if you're given a project, the work will expand to fill whatever amount of time you give people to do it. So hey, this needs to be done by next Friday, and like, guess what? It takes that much time to get done. I think when you look at software and software developers, specifically people who make software, they will expand their application to take advantage of whatever is available. If you start giving a bunch of developers a new chip or more memory or some sort of parallel tasking, they will take advantage of it. They will find a way to maybe generate value for the user, but either way, they'll use the resource. So best case scenario, you use the resource and it's a better application or it does something more powerful. Worst case scenario, it's just going to use up all the computer resources anyway because you don't start optimizing until you have a problem. So I think we're going to see those NPUs, now that they're available. And remember, back to that timeline chart, Apple just unlocked the neural engine for people like me to actually start writing code that runs on it. I know that we're going to have a lot more applications using that next year than we have this year, and I think it's going to be like not too long before Apple starts locking that down and saying, well, we have so many AI things now running that people are like maxing out their phones and it's overheating. So I would be a bad speaker of a startup if I didn't speak about my startup. So Fritz is a company that we started because we saw all of these trends and we wanted to make a software platform that allowed people to use artificial intelligence in mobile apps specifically. And the way that it works is we're just democratizing all of these models into the type of code that any mobile developer can use. So you are able to use something like style transfer with just a few lines of code, or something like object detection or image segmentation, which is the middle one there. But any of these things can be implemented with lines of code rather than neural networks. You don't have to go build your own neural network. You don't have to train it. You don't have to compress it. You don't have to convert it. We just provide all that. And everything that we do runs on the device. So we only focus on pushing things down to, again, where the real sensors are, because we want that cycle to run really fast, and that's where all the good user experiences are going to happen. So all of this stuff is available today. We actually have more features which are on the slide that I could update. But if you are a developer working in iOS or Android, we have a free product that allows you to use any of these things and get started. What we want to do is make people heroes. Like, we want people to be able to use artificial intelligence without having to learn artificial intelligence. And the more of that happens, the more, I think, great applications are going to be in the world, and then that will make us look good eventually. These are some actual customers, so some live use cases. This is a company called Plant Village. It's actually not a company, it's actually a research group out of UPenn. But they were tasked with helping people in Africa, like small sharers, small, what do you call it, farm holders, but people who are growing enough crops for like some of the village. We're not talking about massive enterprises here, we're talking about like, these people, you know, are sort of growing the food supply for the closest ones around them. And in that case, when anything goes wrong, it can go really wrong because they start to have a problem with food production. What they decided to do was train little models on looking at plants and determine what diseases they have, and then provide the information back on how to adjust it. So this is a cassava detection model, and they're looking for actual types of blemishes, like a type of blight that is detectable on the leaves. And they put this 100% on device so that anyone with an Android handset and a camera can be out in the field anywhere. And they're only focused on Africa right now, but they can go anywhere, no network connection, no waiting, just detect every one of your plants that you think there's something going wrong with it, and it will actually not only tell you what it thinks is going on, but what to do about it. Add phosphorus, get it out of the sun, make sure you're giving it more water. That type of stuff is all detectable there. And the net of it is like more people get fed, or rather less food goes to waste, or good things happen. So we love them as a use case. I don't know that we're ever going to make $1 off of this company, but they're doing good things, so we're happy to support them. This is a thing called Superimpose X. And what this example is showing is a technique called image segmentation. So You know, in Photoshop, if I said, take the lasso tool and draw around the outside of the man, you could do it. You're a human. You're relatively, you know, skilled in these sorts of things. But we can train little models on how to do that. And at Fritz, we offer a product people can just plug in, and it will draw that outline around the man. And in this case, they can use it to take the rest of the video and leave it animated while freezing that person in place. So you can create these pretty cool effects. And you've probably seen other things where you know, the background behind someone kind of changes, green screen style. That's the inverse of this. And then this is a form of object detection. It's actually not that dissimilar from the Plant Village example, but this is a company that we work with to sell a proactive type acne solution. And their differentiating factor is the application that they ship with it, which allows you to check progress of your skin. So it's like a 1-minute visit to the dermatologist every week. Take a picture of your face. Let's see how your skin's doing. It's not doing well. Let's up your dosage. Skin's looking better. Let's bring your dosage back down. Stay on the skincare regimen, et cetera, et cetera. It ships product for them. It's a differentiator for them, and it's a better user experience. Like, it's a triple win. Everybody loves this. And we help them create the technology so that all this could happen on the phone. The reason that they didn't ship this before is because if they had to take every picture and put it up in the cloud and then process them all, one, they thought they'd have lower user engagement, and two, they thought they would spend a lot more money, which I can tell you they would have. When you're talking about retail products and stuff like that, like the margin might not be gigantic. They might not have an 80% margin, so they need to be very aware of what their costs and their scale are. This can scale to hundreds of millions of people and cost them almost nothing to distribute. And then every product that they sell is gravy. So the benefits of using a software tool like us is for mobile developers, they could be focused on mobile development as opposed to any kind of ML. So we do everything pre-trained, prepared, simple APIs, fast, easy to use, runs on device. And if you're a machine learning engineer, if you actually build these types of models, we help with the tricky parts, which are like converting them, compressing them, deploying them, iterating on the mobile device to make sure that like you can partner with the mobile developer. We kind of plug that stuff all together in the platform that we call Fritz. If you guys want to play with any of those types of things, well, you can download the apps that you just saw, Plant Village, MD Acne, Superposed X. But we also have a demo app called Heartbeat by Fritz, and that just includes a bunch of really sort of play examples of how you use these types of technologies. But for the developers in the room, that's also completely open source. You can go to GitHub and look at all of the code that's underneath Heartbeat if you're wondering, how do you use image segmentation? You can see it. Okay, start to wrap this up with some conclusions. We're talking about AI first applications. One, and most importantly, AI first, or starting with AI as like a core functionality of your application is no longer a moonshot. It's not something you have to think about worrying about in 5 years' time. You can start worrying about it now. Edge intelligence is going to win inference, meaning if you're thinking about problems that require a round trip to the server, you're probably going to be pushed out with something that doesn't require the round trip to the server, and you're also going to save cost and be more private and give people a better user experience by moving this to the edge. The simple formula of where to start today, and we'll get better, you know, over time, is with any sensor that you have available, which could be one of the ones we covered tonight, or it could be a totally different sensor. You know, literally anything that can give you a piece of data can be used to predict. And 1 minute of an expert's time. At some point, yes, we're going to move beyond this, but for now it's sort of like, what can you train with 1 minute of an expert's time instead of 1 hour or 1 year? This is probably number 3 years where like most people that come to me with ideas break down, is they're like, okay, literally this happened. A friend of mine today said, I got an AI business idea. Okay, what is it? Well, it's a breakup AI. You broke up with someone, you're feeling upset. You talk to this AI and it tells you how to feel better and how to not call your ex and do that sort of stuff. And I was like, that sounds like a psychologist, like a psychiatrist. Like, that's not 1 minute of an expert's time, that's like a lifetime of training to talk you out of your bullshit. Don't call her, don't call him. But that's where people are probably thinking now is like, oh, well, we'll have AI do that eventually. Maybe eventually, but for now, we're not there. And then finally, the NPUs. So where we run this sort of stuff, where we run the edge inference, is fast and getting faster. Apple's in the lead. Okay, we'll do Q&A. I also, these are lapel pins. I'm not wearing one, but they're about this big. If people want one, I have like, I don't know, 5 or 10 with me, so come see me after and I'll give away. But with that said, our blog, heartbeat.fritz.ai, if you want to read more about machine learning or machine learning and mobile, the sort of intersection of those places, our blog is very, very good. And the product is available for free at the free tier. And if you guys want to use that, I encourage you to. If not, thank you. I appreciate you listening, but you don't have to use the product. Okay, cool. Let's do questions. So let's start here.
So you mentioned that one of the services you offer for people developing models is to do some of the work required to get it on the edge device, including compression. Can you tell me what you mean technically by compression?
Yeah, so the question is, if you're a person who trains models, what does Fritz offer, or what do we think is helpful to get it to an edge device? Is that a fair statement?
Yeah, in particular, you use the word compression. I'm curious, I have a particular understanding of that term in terms of neural networks, and I'm curious what you meant specifically by it.
It's a big topic. We could go very deep. I'll try to do the quick one. So there's a couple of runtimes that we work with right now. One's TensorFlow, the other one's CoreML. CoreML is Apple only. TensorFlow runs on a bunch of different things. We help people get their models to fit into those formats. Those are runtimes. They don't have every operation that a training environment has. So you have to make intelligent decisions around how you created your model in the first place, knowing that it's eventually going to end up on a device that's running on one of those platforms. So that's the first thing we do, is just to tell you problems that are going to happen in conversion. You can't use this layer type is inefficient, fully connected layers are incredibly slow, don't do that. Like, that's sort of guidance level number one. Number two are the current optimizations that you make. So things like quantization. Typically when you're dealing with matrix multiplications, you're using floating point numbers, so like numbers that are represented by lots of decimal points, and that turns out to take up a lot of space and take more time to do the math on. So we convert those all to integers, and you do this thing called quantization where you kind of put them in buckets. And that means that you can make a model a lot smaller and run a lot faster because you're just dealing with these sort of integers and a fewer number of them. So that's a way to make a model smaller and faster. And then we're not delivering this as a product yet, but we're working toward some of the cutting edge, which looks like very aggressive pruning. If a neural network has lots of connections between it, cutting edge research shows us that you can cut out about 65% of most neural networks without affecting the one prediction you want to make. So okay, envision this as you have a brain, and the brain is connected to a lung. And all you're trying to do is keep the lung breathing. You don't care about vision, you don't care about motor movement, you don't care about memory. How much of that brain can you cut out? And the answer is a lot. I'm not like a neuroscience or anything like that, but from what I understand, there's a lot of the brain that doesn't do that thing, right? There's like one little part that's got the lung moving. Same thing is true of most neural networks. You feed it 10 million pictures of people, and it determines all sorts of interesting patterns around colors and textures and depth and space that mean nothing to tell me whether that's a person or not. It's just a bunch of crap that gets loaded into the model. And currently, we don't care that much. We sort of say, all right, well, we can get it to a reasonable number of megabytes, ship the whole damn thing, it's fine. But we're moving toward a world where we want to train it on, instead of 10 million images, 300 million images, and we want to get rid of as much of the crappy connections as we can, and that means that we do this aggressive pruning. So we go from 100% of the connections down to maybe 35% of the connections. So those are some of the optimization techniques. That last one is sort of like cutting edge stuff that we're not delivering yet, but the other stuff we do. Sorry, we'll go there because I saw you earlier.
What are the limits to edge intelligence as far as, given that so much is dependent on interconnectivity with other services, like you need to make an API call, you have some model that predicts something, but you need some external input, so you need to make an API call to check what the weather is, or what inventory is in stock from the central system or something. So obviously, as you pointed out, you can pre-train, you can pre-install models, but as far as dealing with these external inputs, how would you go beyond our current deployment model to handle those things?
Yeah, so I think one way to state that question is like, what do you do when you want to be edge intelligent, but you're dependent on information that comes from elsewhere? And then there's other types of things. Well, sometimes it's just like tough cookies. Like there's some cases you're just not going to be able to deal with that. But I believe over the longer term, we'll see an inversion of things. So it's a lot easier for me and faster for me to use a network connection to send down a piece of a string of data or a couple of numbers than it is for me to push an image that's 12 megapixels up to a server. So we'll probably end up doing, if we depend on external things, we'll either be making those calls, and that will be network bound, which will still be faster than if you push the large thing up and back down, or we'll do stuff like we have lots of caching and local references. So if you look at like that Google Shazam type home screen thing, they keep a local database of 75,000 songs. that's one way for them to not be dependent on the network. They could easily take the current hash of the song and send it up to the cloud, and they'd have a database of 2 million songs that they could search through. But that's not like the user experience they want. They want it to run locally, they want it to run faster. So certain things, yeah, we're not gonna be able to do anything about, but whenever possible, we're gonna move all the information down. And that is still completely ignoring the fact that like where you train the model might be in the cloud and have everything available to it. So you might be able to actually sort of train these models with a lot more inputs and then predict just on one input. So you sort of make a more complex model that's trained on a bunch of information, and then on the device you maybe only have one piece that you can draw the vector from, but like from there you can still get a pretty decent prediction. State of the art in this stuff is still in like the 80%, but once you get to 95%, that's when things start to feel like magic. You just go like, oh, wow, okay.
I have a couple of questions. So first, you showed the code snippet. What do you use for your stack of languages? Is it like Scala-ish, or is it Python TensorFlow? And by extension, what does Apple prefer on their unit? And the second one, do you do any type of federated learning for your edge devices, or is it mostly inference?
Yep. Okay, so the first question, like what is Fritz technology? We have SDKs in 2 places, iOS and Android right now. We're going to be building additional hardware platform support in the future, but for now, in Apple land, you can either use Swift, which is what that code was that you were looking at, or Objective-C, which looks a lot uglier, which is why I don't put on the slides. We have an SDK that works in either one of those. So that's the Apple side, and then on the Android side, it's all Java. So Android's a weird use case, and you can ask Oracle whether they think it's Java or not, but the syntax is Java, and everything is written just the same way you write any other Java. Underneath each of those things are the runtimes that you actually execute these models on. So on Apple, we use CoreML and CoreML 2, which is the latest generation. And then in TensorFlow, there's TensorFlow Lite and TensorFlow Mobile. And Google being Google, both of them still exist, and they keep pushing forward different features in each one. Like, even though they think that they're phasing out TensorFlow Mobile, it still does a ton of things that TensorFlow Lite can't do. So for now, we basically have to support both. At some point, maybe we will support fewer. And then the second question was federated learning. So for those of you who don't know, there's a certain type of technology on the training side called federated learning, which is essentially saying, send a small, relatively naive predictive model down to a device. And then based on what happens on that device, let's update that naive model to get better over time. The canonical example of this, there's a paper published which people can read if you Google this, from Google with the predictive keyboard. So what they did is they sent down a small model that was like, if you were typing, I will be, what's the next word going to be? I will be home, I will be tired, I will be happy, I don't know. And they would let people tap on one of those predictive suggestions, and based on how many people predicted which one of those was right, which one of those 3 options was right, they then sent that information back up to the central cloud service to say, when people type I will be, they most often mean home. So the next time you make an update to that model, just rank home as the most likely outcome, so that shows up as the first predictive option always. But the other cool thing about federated learning is it can be customized and changed completely per person. So like a recommendation system, like an Amazon type thing, might show products that only you would be interested in based on the stuff that you have bought. Same thing can be true of these federated learning models, that they get down to the device and they are made to accept new data that comes from just one person, you. I guess another reasonable example of that is like Face ID. That model is sent down with how to look at a face. It's definitely not sent down to understand your face, so you have to train it on your face. And that stays on your phone in local storage. Apple does not federate that, right? And they also have no interest in learning about how you would average everybody's faces together because it does no good. But that's what federated learning is, and we don't do any of that at Fritz right now because almost everything we're focused on is inference. The actual training phase and the collection of the information, we're not seeing that many people that need to do it. Google wrote that paper and like that's it. You know, there haven't been a lot of other use cases or people saying, well, using the federated learning, we've shipped X. It's kind of just people at research stage for now.
Question 1 is why Fritz. Question 2 would be going all the way back to the beginning about databases and optimizing intelligent databases. Could you talk more about that? Like who's doing it? How soon you think it'll be common?
Are you asking why Fritz the name? Well, naming things is hard. So we basically wanted something that sounded sort of new and interesting, and we could get a 5-letter domain, so there's just not that much to it. Just a cool name. And I'm half German, so like, sounds vaguely German. Okay, the second piece, the database. It is a great question of when that will become commercially available technology. I would be surprised if it wasn't already in use inside of Google, or perhaps Amazon. I don't know when it's going to be productized because they tend to be laggards on that sort of thing. If you look at like Google Cloud Engine, Google Computing Platform, GCP, they built all of those resources for themselves internally, and they use them to great effect as sort of a competitive differentiation, but they never productized them. Amazon was kind of the opposite, where like they just immediately productized them and they started making a lot of money. So Google probably is doing it now, and they probably have a certain number of indexes that are based on AI lookups at this point, but when it will be available to you or me through their services, I have no idea. Another possible outcome would be, so we used to have 2 open source databases, right? You used to have MySQL and Postgres, but then Oracle ruined MySQL, so now we just have Postgres. So it could be that independent, developers would start developing this kind of, like a neural index inside of Postgres, and we might see that in one of the future releases. I haven't checked their like bug backlog or their issue backlog to see if anybody's currently working on it, but like that's the other place I would look for it. Another option actually is something like Snowflake or something, sort of one of the independents doing it, but like I haven't heard anything about that either. This is still research. Sorry, let's go here.
Just want to thank you again for this very interesting talk tonight. And also my question is, a lot of this applied machine learning out there is still black box models. And there's a subfield of machine learning called MLI, machine learning interpretability. There's also a thing called FAT, ML, fairness, accountability, transparency. What's your opinion or take on that, and thoughts on that?
Yeah, so what he's rightfully pointing out is there is still, it's very true if you say, this is what the model can predict, and then you say, how does it know that? And nobody has the answer to that. We sort of understand the architecture of how all of these little, fake neurons and stuff are linked together and how the convolution layers are set up. But then we're like, okay, tell me exactly what happened with that prediction that got to that conclusion. And we don't know, in the same way that like we're still mapping out brains, in humans, and we've had access to those for a lot longer. It doesn't worry me that much knowing that the scope of what these models is capable of doing is still relatively limited. The fairness and accountability stuff, like it doesn't come into play in my work at all because we're building stuff for like user experiences based on phones or vehicles or autonomy and that kind of stuff. We're not working on weapons systems. We're not working on sort of geopolitical machinations or anything like that. But I'm sure somebody's working on those models, right? Those guys over at Palantir are probably like, based on all the data we fed in, like we can tell you which of these 6 million Russian people are probably spies in the Americans right now. It's just like, well, that might end up with someone getting killed. So like, be very careful doing that. And if you don't know how to say, this is how we got to that prediction, these 6 million people should go be like smoked out, like that's scary. So personally, I just stay the hell away from those domains. But in terms of accountability, I think we need to be open to when things are actually being powered by like neural networks and by things that we know that we don't understand the root of, and then only use them in the right application. I think at some point, we might get better at giving people the sort of traceability and like path through a neural network where you start to feel more confident that like, okay, we can use this in this way and we can show how we got there. But I think that's harder. I think that we're farther away off. And also like, people are really bad at multiple steps. If I showed you a flowchart that had 14,000 decisions on it, you would give up at like, 200. So even if I could show you the flowchart, I'd be like, here's exactly pixel by pixel what happened that determined that this person, was this person and that we should go send a police officer to the house. You'd be like, yeah, I'm not going to be able to process that. I mean, like, you're human and you have sort of human level understanding of that stuff. So I think at this point, best off just stay the hell away from those use cases and to police the people who do that to make sure that they have, the right sort of accountability for getting it wrong. Sorry, right, Beth.
Okay, GPUs are limited in the problem set that they're appropriate for. Is there some limitation like that for these NPUs?
Yeah, absolutely. So a GPU is limited to certain types of matrix math that tend to go well with graphics, graphics processing unit. And tensor processing units, or TPUs or NPUs, tend to be good at the type of tensor math that goes into neural networks. So if we move to some sort of different architecture that was less dependent on that type of math, then yes, those chips would be they would not be an advantage anymore. So far, I don't see that happening. It looks like the building blocks we have in place for network architecture are going to continue to be the same building blocks. The layer types that we use, the way that we put them together, they might get bigger and more complex and do more, but the underlying operations, the operation set you need to support doesn't look like it's going to change. And if you look at like, CPUs, it was sort of like, take this thing, put it in a register, add it to this other thing in the register, put the result in the register and move it through. Like, we're doing the same thing, but just very specifically for these neural networks. As the underlying instruction set changes, that's when we should worry about those things becoming a bottleneck. But so far, so good. And I think we've got, decades before that really would change. The next jump for that sort of thing might be like, I don't know, I'm not like a quantum mechanics researcher, but if we start to see quantum processors where you can sort of search the entire option field of all multiplications and pull out the predictions, like that might fundamentally change things. But we can't run those types of quantum processors without like liquid helium at this point, so like they're definitely not gonna be in your pocket. So for now, NPUs seem to be the best. All right, let's do one more, yes. Or maybe two more, we'll go to you last in the back.
A little more on like the design ideation. Like, how do you decide on what's next? Like, what are you going to provide to the developers? What API or model you're providing?
Yeah, that's one of the hardest things. For us to decide what we are going to invest in productizing, so making available via an API or an SDK, part of Fritz, that's one of the hardest things we deal with. I wish I had some like really thoughtful, like high-level formula for you. Like, oh, I do this, analysis on my whiteboard, and then I figure out the right answer from it. It's actually a lot more based on what we think is going to provide the most wow. Like, what do we think people are going to be impressed by? How hard was it to get there? If it's really hard for us to get there, and we spend all day working on this stuff, and we're experts in the field, then we know most people aren't going to get there. And therefore, we know that there's going to be a bit of wow that comes with it. So we started with things like, style transfer, and then did image segmentation. Now we're working on some stuff in pose detection. So actually looking at a human, not just is there a person or where is the person, but like how are they holding themselves? What direction are they moving? How fast are they moving? That kind of stuff. We think that kind of unlocks like a whole new dimensionality to the experience. That's just us sitting around a table deciding. There's really no great formula for it. One thing that you do have to factor in is like what can be had. We don't do bleeding edge research. We're not an institution that can spend all day iterating on different model architectures. So we tend to start with stuff that came out of a lab. So Stanford, Carnegie Mellon, Waterloo, et cetera. If they have published a paper talking about pose detection, we can start with that and we can build on top of it. We don't usually go and say like, wouldn't it be great if we could figure out like retinal scanning with a camera instead of a different type of sensor? Like, we're just not that kind of team. Maybe someday. I would love to have a research lab eventually at Fritz, but for now we just base our work on other published things that maybe haven't been implemented and definitely haven't been built for edge and mobile together. So that's our moat. All right, last one, all the way back.
I was wondering more about the organization of people. So in terms of taking advantage of NPUs or edge computing, is there any opinion you have about what else?
On what makes like NPUs grow? Or
if I were in an organization that could benefit from using them, like what sort of organization should be your composition of people?
I think something's never going to change, which is like, what problem are you solving and who are you solving it for? And if I can make a case that there's an intelligent way to solve that problem using artificial intelligence or something, like you're more likely to get it sailed through approval than anything else. There's also a lot of buzzword stuff that happens these days where people are like, I would love to say that we're doing machine learning instead of doing statistics because it just sounds better. People listen to it more. But really, it's just got to start with like, what experience are you delivering and why? We do a lot of stuff with companies like, Plant Village or Superimpose X that they just couldn't have done. Like, it would not have been possible if they weren't able to get this technology in a small enough package to be deployed and like at an affordable price that they can actually get it into the user's hands. So, yeah, I don't have any like magic bullets or anything. It's just sort of solve a good problem and then have a useful explanation of why an intelligent version of that would be better than a not intelligent version of that, and then have the skills and the access to the information and the models and the software you need to make it happen. I mean, if you think about it, like, we've already done this. It's history repeating itself. We started with, web 1.0 and 2.0, we're really just taking like offline processes and making them online. You know, we would say something like, okay, you're Hertz rental car, and you currently have a database of where all your rental vehicles are, and you have a terminal sitting in someone's office, and it connects to that thing. And it's like, what if we put that all on a web application? Well, that seems like an improvement. Like, we wouldn't need that server, and we wouldn't have to like be bottlenecked by our own shitty network connection going down. If people were able to argue those use cases successfully, I think we can do the same thing now and say there's a better, more intelligent version of our photo editing tool, or our, you know, our experience that we want to deliver is one of autonomy, and there's just no way we can do that without computer vision and being part of it, that kind of stuff. So I think these transitions, like, they happen every 10 years or so, and people eventually just start asking instead of being told. All right, cool, we'll wrap it there.
Yeah, let's put a round of applause for Dan.